Next will be a second problem, lineup counting queries. The same statement, but slightly different queries were also in bronze division. So if you didn't solve it, you can kind of say that you couldn't solve a bronze problem. Well, that one was a little bit easier. In that problem, you needed to answer queries of given time and the cow ID. You need to find its position, the current index in the sequence. That was one type of query. And also given time and position, you need to figure out the cow ID, the cow that is right now at this position. I think that that problem is not trivial, and it's a nice introduction to this one. But yeah, that's not what we're doing here. We have some process, and we need to, at some time, which is up to 10 to 18, count the given range of cow IDs, how many of them are in this range of positions. You can, if you want, later watch the analysis of bronze problems to see some extra stuff about this. Here, just in short, I will say this. We can implement a simulation. This was bronze, and it was, what was the name? No, so maybe that was in silver. Yes, sorry. Sorry that I told you that you couldn't solve bronze problem. It was silver problem. Yeah, we can run this and output some number of lines. This is hard to read, so I will save to a file. Open the file. Okay, I made my code so that the numbers would be nicely in columns. If something has only one digit, then I put extra space. Now, one thing you could do is look at a line, let's say some big line, this one, and you can try to observe a pattern. In this line, with numbers up to 34, numbers up to 17 are mixed up. Numbers from 18 up are nicely here. Then I see that number 17 is here, 16 is here, then 15, then 14, and the distance is 3. Then after that, 11 is there, 10 is here, which seems to be 4 units to the left. But then from 10 to 9, we have more units because it's 5. So it's very irregular. It starts being ugly. That being said, I think it's true that among the remaining numbers, so if you ignore bigger numbers, then the distance will always be 3, I think. It's not exactly needed in the solution. At least there exists a solution that it doesn't use the fact, but I think that's the case, that you can here analyze this part, and you can say the biggest, so in this first half of the 34 numbers, what you have is at some position 17. That's always second position from the right. Then 3 units later, you have 16. 3 units later, you have 15, and so on. And then when you're out of the sequence, you roll back here, and you always skip, you go to the third available slot. So maybe if the 15 is, sorry, like 11 is here, then 1, 2, 3, 10 is here. So one possible approach is in this sequence, if always among a big number of slots, if you always take 1/3 of them, so you start from some big number, let's say from this one, and you process this from right to left, and you take every third slot, you're kind of multiplying this by 2/3, and the remaining number of slots is this much. If you process again, it will be this much, and this much, and so on. So after logarithmic number of steps, you will be left with 1 element or 0 elements. That logarithm is around 100 something, 100 plus a little bit. That's a logarithm of base 1.5 of 10 to the power 18. That's the number of repetitions you need. And you can try to process that. I think it's a little bit similar to Josephus' problem. You will find it online or in CSES. I see some similarities. So I think that's one possible solution, to just now try to do some math with that and try to understand first with this every third element. If I want to take away every third element, how many cows of my allowed range are within the allowed range of positions? That might be ugly. I don't know. I didn't analyze this way. Instead, second possible solution, and that's what I will discuss, is if you look at this sequence and you look at a particular value, like let's say 6, you will see that for some time it stays in the same slot. Then it keeps moving to the left. Then it resets to the half of the sequence. Then it keeps going to the left. And then after getting to position 0, it again resets to the half of the sequence. I think we can better see it if we only output, let's say where number 6 is fine, where number 6 is. So let me run the program again and refresh the file. The 6 follows this nice pattern, very simple pattern, and the same happens for other problems. Sorry, for other numbers. So at time 6, the 6 is here at the end. At time 11, which is twice 6 minus 1, it's here. After 6 more steps, it is at the beginning, and at time 18, it resets to the half. Then, because it resets to the half, that's position 9. After 9 more steps, which is 27, we are at the beginning. And because of that, at 28, we are again in the middle of the sequence. So roughly, you can again say that this is time x, then this is roughly time x times 2 over 3 plus 1. Which means that whatever the initial number x is, it will be times 3 over 2, not 2 over 3. You need to multiply it by 1.5 at most logarithmic number of times, 100 something, before you run out of time, before you process all the 10 to the power 18 seconds. So lemma, every cow resets. The reset is from the beginning of the sequence to the middle, O of log times. And it's predictable / reliable where the cow is after every reset, and we can keep track of her. So if I focus on cow 6, I can figure out using, after let's say 4 resets, I can compute where she will be in like 4 operations of multiplying by 1.5 with proper rounding up or down. So the task is that in some range, I want to figure out the number of cows of some values. So tracking a single cow doesn't do the job. But for every cow, it's very important. It's very important where she will be. And what I'm going to do is, because the number of resets affects the math heavily, I will iterate the number of resets that happens. My main idea for a solution, it will be for every number of resets from 0 to like 140, I want to here count such cows in ID range L1, R1 that they are in position range L2, R2 after time t, after exactly that many resets. Let's call this variable z, after z resets. Because the number of resets affects the math heavily, we can, given the number of resets, we can express where the cow is in terms of some formula, but rounding is annoying. Actually, maybe it's not a good idea to say that cow x, where she will be exactly after time t, Again, because the rounding is annoying. So I think whether x is even or x is odd, it might affect what happens initially. So maybe I will look at it in a slightly different way, which again, if you solve the silver problem, you would know how to do it because the silver problem consists of two parts. Analyze where the cow is, but also analyze for some position what cow is there. Because the alternative here is to do the following analysis. We can focus on some position and we can, this position X, and we wonder what cow gets there, what cow is there. So whatever cow is there, she's also here, she's also here, she's also here, she's also here. And when we get to the middle of the sequence, we reset. So the cow apparently is here, then here, then here, then here, and here. And eventually we'll get to such position that we can say that she's here and it would be 4. I think the math here is not exactly right because this is not the perfect middle of this sequence, but it's roughly like that. You can, for a cow, keep tracking back. And so given the time and position in logarithmic time, we can figure out what cow it is. Then what I claim is that maybe I will roll this back. I want the output with the big numbers. Refresh this file. Okay, thank you. The task says that we need to look at some time, at some position of indices. And for this position of indices, I want to figure out what cows are there. And as I told you already, we will iterate the number of resets, which basically means, again, maybe I will do some new lines. For this range, what I'm doing is I'm distinguishing few separate sequences that are very regular, and I'm counting them separately. For example, the cows that resetted 0 times, so they never got to the beginning, those are cows 16, 17, 18, 19, 20, and maybe 21. This is the every third position from the middle to the left. The big values, close to time over 2. But what is here after 1 reset? Those are cows, I'm guessing, 13, 12, 11. Okay, but how looking at the full array is supposed to help us with that? Assuming that something resets, let's say 0 times. Whoops, I don't know where I was. It's not good, sorry. Let's say that I was here. There is here this 16. There is here. Maybe I will increase the font. Oops. Okay, we are here. Where I'm investigating cows that resetted 0 times. If 0 times, then I can keep track, I can shoot straight up and right, get to the middle, and I will figure out what is the cow or the minimal cow that matches this description. For the math in your code, also it might be easier to shoot left and down. So from here, go there, and also you can look at the cow that is here. So after one more transition, she would be in the middle. That's the idea. Now, let's not look at numbers, let's look at the drawing. There is this pyramid of values. Let's also mark the middle. We get a query about some range. In a range, we need to count the number of cows that the ID is also in some range. First of all, this part to the right of the middle is trivial. This is very easy. Easy to compute because the cow there, the ID is equal to the position. Very easy to handle. We now only focus on the part that can be to the left from here. So let's say something arbitrary there. Let's say that I want to count cases of cows that resetted exactly twice. So I say the following. Whatever cow is here, I can shoot whatever math is more convenient for you in code. You can shoot this way or you can shoot this way and do the math from that. Or maybe, so if I'm here, then also I'm there, here. How many resets I said? 2. So one more. Here, there, there. Okay. So there is here some cow ID. There is ID, or this row number. That is the cow that would get there. Sometimes this, what I'm doing as I keep going back is basically I'm dividing by 2/3. And sometimes this math will not be exact. I mean, we cannot exactly multiply by 2/3. We need to round. And because of that, my goal isn't exactly to compute the cow that gets here and is there after exactly 2 resets, because there might be no cow that is here after 2 resets. Maybe the cow here is after 1 reset or 3. What you're computing here is the smallest possible cow ID that satisfies that. So you want to know that for 2 resets, there is some range of cows, maybe from 8 to 10, that indeed get here. And your goal right now is to compute the value 8. You want to say that cows, for 2 resets, the cow ID needs to be at least 8. Similarly, you focus on this position and you do same math. And you will get some other limit, like cow smaller equal 10. And from that, you want to know, okay, so now you intersect this range with the range given in the input for the cow IDs, and you then will know that many cows might be here after exactly this many resets. And this, if we look here, is always equivalent to investigating one of those regular sequences. Like here, one of the regular sequences is 7, 8, 9. This is the sequence of cows here on the left that are here after 0 resets. For every such regular part, you compute the lower bound and upper bound in your range. To be honest, I did not implement this problem to verify the exact rounding of +1, -1. I have the convenience of being kind of retired from competitive programming, and I don't need to suffer from those off by ones. Again, in the USACO Discord server, I've already seen somebody pasting a nice code, so we can go there. I don't want to show it now because it's not my code, it's theirs. I didn't ask for permission, so just look it up. And as always in usaco.org website, eventually there will be code. But depending on what exactly you do, I think it's very easy to achieve the bad time complexity of, for every query you can do logarithm times logarithm. If for every number of resets, you here also do another internal for loop that, for example, it multiplies by 2/3, it's not a great idea. You might get time limit exceeded. So what you want to do is realize that the operations of doing this for every number of resets, those are same operations. If from this left point of your range of positions, if you try to see where you are after 2 resets or where you are after 5 resets, you're doing the same thing. So what you should take is you should take this. I'm talking some implementation detail that affects both runtime and the convenience of your code. If at time t, you are here at position p, then equivalently I can say that after how many steps will you be there? After p extra steps. So this is t plus p, right? If this was 5 units to the right, then you need to go 5 extra units down to be here. So I claim that if this is t times plus p, then going here to the middle and going there, what this will be is t plus p multiplied by 2/3. What you want to pre-compute is your time from the query plus starting position allowed, which was L2, So t plus L2, you take this value, you multiply it by 2 over 3, 140 times, and you save this array and you use it. Same thing you need to do for this right endpoint. So also you need to do it for t plus L2, t plus R2. And I'm not sure if for t itself is needed. You can think about it. Homework, the details are homework for you, the viewer. I've seen in the code that they also use this. I'm not sure if it's necessary. Maybe it's redundant. Not sure. But once you computed that, you will, in constant time, for every range, for every number of resets, in constant time, you will get a bounce. So you can multiply this by 1, and then for sure it's accepted. Well, unless it's wrong answer because of some mistakes in math. Okay, that's the solution. You iterate the number of times the cow resets. And for every number of resets, you figure a possible range of cow IDs that has that many resets. Do you have any questions? If so, tell me.